Hey guys, I'm extremely excited to finally be able to share with you what the team at Krontech and I have been up to for the last few years. This is a brand new camera built on a brand new architecture. This is the Chronos 4K12. It records 4K resolution, 4096 by 2160 at 12 gigapixels per second, so just under 1400 frames per second at full resolution. This camera is just one in a line of new cameras. There's also the Q12, which records 2048 by 2016 at just under 2800 frames per second. I'd like to give a shout out to the entirety of the Krontech team for making this possible. This has been an amazing and long journey, and we are finally here. Thank you so much. In this video I'm going to give you an overview of the camera, a quick demo of what it's capable of with some demo shots, and then I will take it apart and show you what's inside. So without further ado, have a look at what the Chronos 4K12 is capable of.
Time flies. Capture its wings with Chronos 4K12 by Kron Technologies. Embrace the art and science of slow motion with 4K video at over 1000 frames per second. No matter the subject, from research to creative, wildlife to sport, Chronos 4K12 records an unparalleled detail and speed, portable, intuitive, and designed to give you mastery over time like never before. A built-in touchscreen for ease of use, flexible record formats, all with the portability of a point-and-shoot camera. Its value for performance is unmatched. It's about time high-speed videography was available to everyone. Order, unbox, power on, and start shooting. Review and store your clips directly inside the camera. With Chronos 4K12, it's time to focus on the subject, not the setup. Empower your creativity, capture new data, redefine what's possible. In a world where every moment counts, capture time like never before. With Chronos 4K12, it's about time. Order yours at www.krontech.ca.
The 4K12 and the Q12 are available for pre-order on krontech.ca right now. Expected to ship in February for the 4K12 and March for the Q12. This camera builds upon the legacy of the Chronos 1.4 and 2.1. They are similar in size, a little bit bigger for the 4K12, mainly because it has to fit a full-size LR DIMM, but that does allow us to offer 64 and 128 gigabytes memory capacity, so the record time, even with a much faster pixel rate, the record time is about the same as the 2.1. Both of these cameras are based on the G-Sprint family of image sensors from G-Pixel. The 4K12 is based on the G-Sprint 4510, and the Q12 is based on the G-Sprint 4521, running in binning mode. So this sensor has a pixel pitch of 4.5 micron, and the Q12 has twice that at 9 micron. The I/O on the new camera has been greatly simplified compared to the 1.4 and 2.1. Power input is changed to it's the same size of jack, but it's now 12 to 24 volts, so you can use DTAP and other external battery packs to power the camera. That's the one thing this camera really lacks from the previous cameras, is the internal battery. It's just really difficult to get enough battery capacity in something this size to get a decent runtime. This takes about 35-ish watts, and the legacy cameras take like 15 to 20 watts. With a 100 watt-hour DTAP battery, you'll get about 3 hours runtime or so. The trigger has been simplified and combined onto a single 4-ring TRS jack, as opposed to the old cameras that have split across a BNC and this pluggable connector. The USB has been significantly upgraded. There's 2 USB-C ports. Port 1 can support device or host, so you can either connect it to a computer or to external devices like a hard drive or USB mass storage or Ethernet adapter or that kind of thing. This port connects directly to the PS side USB in the FPGA. Port 2 is port 1 is capable of 5 gigabits per second speeds. Port 2 is on a PCIe to USB-C bridge by AS Media, and this one is capable of USB 3.2 speeds, so 20 gigabits per second. And HDMI is also supported for video outs, and that does it'll do either 1080p 60 or 4K 30 outputs. On the other side, we have maintained the SD cards. There's a full-size SD card for saving video and a system SD card that holds the operating system. This means that if there's ever an issue with the firmware, or it gets corrupted or fails during an update, you can just take this card out, reflash it yourself, put it back in. There's no need to send the camera in for service. It's very basically impossible to brick. And in addition to this storage, there is an internal 1 terabyte SSD that can be used for saving video. The lens mounts on this camera are user replaceable. You can simply unbolt this plate and take it off and change it to different mounts. At launch, we're going to have C-mount, MFT, Micro Four Thirds, as you see here, Nikon F, Canon EF, and Sony E mounts. This will surely make for an interesting teardown because it is the first product from Krontech that I'm tearing down that I haven't designed myself. The previous products I had done the mechanical design, and this one was done by the team, so I have a little bit less intimate familiarity with how it's built. And this is the first time this is actually the first time I'm doing a proper teardown of this camera. So let's see how it goes. There we go. Yeah, if you've seen the previous teardown, this is quite familiar in terms of construction. And as Dave Jones would say, we are being mooned. There's not many components here. It's mostly all the active stuff's on the other side. Just some power management parts, connectors, and lots of thermal pads. The camera you're seeing here is the revision 2 of the beta. We actually just shipped sent the boards for the next revision. Basically the release candidate out just a couple days ago. But yeah, this has a lot of, there's a lot of thermal pads on this. It's we kind of just put them all in. We haven't fully done all the thermal testing to determine which of these are needed. But hopefully the final production one will have a little bit less thermal pads. Okay, so these are the connectors for the 2 fans. And then, let's see, I think we need to, there's probably, I'll probably take out a few screws around here as well. Yeah. There we go. Just a bit of effort to pull off the very large multi-pin connector that goes from the main board to the sensor board. And oh, I've forgotten the this one. That should come out now. There we go. Perfect. And here's a better view of the inside of the case. I've got sort of a cross-flow ventilation scheme with push-pull fans blowing air across heat sinks on both sides. These the fins on this sort of interleave in between the fins on this one. Thermal management was much more a consideration in the design of this camera compared to the 1.4 and 2.1, as it dissipates almost twice as much power. Yeah, this is there's a heat spreader and heat sink here that covers up most of the main components, and the cross-flow ventilation also cools the memory sticks. Let's continue pulling this apart, and I will talk a bit more about the design. This board handles all of the trigger I/O and protection for that. It's not too much. It's pretty much the same trigger I/O circuit from the 1.4 and 2.1, but 3 of them. And then I believe this screw has to come off so that the SSD can sort of stay in place while the heat spreader comes off. Thermal pads are holding it in place. Double check I didn't miss any screws here. No, that looks good. There we go. SSD out. And there we go. At its core, the 4K12 is based around a Xilinx Zinc UltraScale Plus ZU7EV FPGA and system-on-chip combo. This basically has it's basically a combination of the two halves of the Chronos 1.4. Like the 1.4 has a system-on-chip, kind of like a smartphone CPU with RAM, as well as an FPGA that handles the high-speed data acquisition from the image sensor. And the Zinc combines both of those. In this case, it has a 500,000 logic element FPGA, as well as a quad-core ARM Cortex-A53 at 1.5 gigahertz to run the user interface. I can show you a quick block diagram of what's inside the Zinc here. It basically has the two components, the PS, or processing system, and the PL, or programmable logic. Working with AMD Xilinx on this project has actually been really fantastic. They've been extremely supportive of the whole team and us on the project, and they seem to be really impressed with what we're doing with it. One of the senior directors we had met with was impressed, and they're going to be showing the 4K12 at their trade show booths as an example of what the Zinc is capable of. Apparently we're using much more of the functionality than most people ever use in these chips. There are two large memory interfaces on this. The PS side connects to this. These are both DDR4. The PS side connects to 8 gigabytes of RAM for the to run the Linux operating system. And then there's a large LR DIMM, also DDR4. This can be either 64 or 120 gigabytes, and that is the acquisition memory to store the uncompressed high-speed video. Earlier on in the design, the PS side memory was originally going to be chipped down. That's basically when you just put the memory chips on the board and not have a module like this. But we changed it to a module to get some more space for some of the connectors underneath. And it's also generally just cheaper to buy these modules. The board I'm showing on the overlay here is an early prototype of the in-camera board. The top section is the in-camera board itself, and the bottom is basically a test coupon that has a bunch of debug hardware and things to test some peripherals on the FPGA. That way we could both prototype something close to the final form factor of the camera board and have access to some extra FPGA features that wouldn't be on the board to do initial or sort of early testing and debug. LR DIMM stands for Load Reduced DIMM, and this is basically server memory. What differentiates this from regular DIMMs, or dual inline memory modules, are some buffers. There's a buffer here that buffers the address and command signals that are sent to all of the memory chips, and there's also buffers on the data bus. This is all for the load reduction. That basically allows you to put more of these memory modules in on the bus to have higher memory capacities in servers. Taking a tour of the rest of the board, we have an MSP430 microcontroller and an I/O expander. These basically form the power management controller for the camera. These do things such as sequence the power supply turn on and turn off for all of the different power supplies. There's many well over 10 power rails on this board, and they have to be turned on and off at in the right order. So this accomplishes that. It also accomplishes some low-level functions such as regulation of the fan speed and thermal regulation of the temperature of the camera. There's a flash memory that's for storing calibration constants and things that you don't want to stop existing if the user needs to reformat or reflash the system SD card. There's a few random power supplies. There's some oscillators generating clocks for the FPGA. A bunch of power supplies, linear power supplies. These are for provide some clean analog supplies for the MGT or multi-gigabit transceivers. Those are that's the part of the FPGA that generates the high-speed serial signals for interfaces such as PCI Express for the NVMe and the high-speed differential signals for the for USB. Some more USB support things. There's a USB 2 transceiver. While the USB 3 signaling for the 5 gigabit signaling for the USB 3 is generated by the transceivers, the USB 2, which is also required for operation of that, can't be. So there's basically a USB physical layer chip, or PHY, here. There's also a bus multiplexer. This handles the switching of the diff pairs, because if you plug the USB-C in one way versus the other, you have to switch around a couple of the pairs, and the Zinc doesn't support that, so you have to have a chip to do that. And up here is an HDMI video retimer. Basically, this takes the relatively sort of low amplitude signals coming from the MGT and buffers them to higher amplitude to drive the long cable. And then there's some more supervisory circuits, like some input protection and filtering, some clock redrivers, and of course the big 400 pin connector that contains connects to the sensor board. This has power and 92 channels of LVDS signaling, plus 4 clocks and some other signals. On the other side of the board, there's a lot less. Basically just a bunch of power supply components supplying various power rails for the camera. And the other big part is an AS Media USB 3.2 host controller. This bridges an X4 PCIe to the USB 3.2 port with 20 gigabit speeds. Let's get the front of the camera apart and take a look at the sensor board. Yeah, these lens mounts are user swappable. Many people want different lens mounts on the camera, so we decided just to make these, sort of integrate that into the design compared to the previous camera, which was just C-mount, or a CS mount. So yes, the user will be able to take these plates off, put other versions on. They can also, there's also a set of shims available. You can put different thickness shims in to adjust the back focus, which is effectively the distance between the flange of the image sensor and the or flange of the lens and the image sensor face. So lenses, especially basically, you have to set this correctly in order for the lens to focus correctly, especially zoom lenses. The IR filter is also user removable, and you could change to different filters for certain scientific applications. And there you can get a nice view of the face of the image sensor. The reason both the IR filter and the window in the case here are larger is to accommodate the Q12 variant, which uses the pin-compatible but physically larger G-Sprint 4521 sensor. That way, there's a commonality of all of these parts between the different cameras. Okay. That is now off, and let's get the screws out of here. There we go. There we go. Nice big ceramic package on that. Don't see that too much these days anymore. There we go. The sensor board itself basically just consists of the sensor and a whole bunch of support circuitry, mainly power supplies. There's a couple of 8-channel DACs, some quad op-amps used to generate some bias supplies, as well as a whole bunch of linear regulators and a few switching regulators to generate low voltage supplies to feed some of the linear regulators so that they don't dissipate so much heat. And on the other side of the board, there is really just some bypass caps and the large pin grid array of the sensor itself. And you can see there's a thermal pad down in there, and on this side there's a part that's a little protrusion to meet that thermal pad, as well as some more to help conduct some heat through the pins and into the chassis. This sensor is relatively power hungry, dissipates about 5 watts at full speed, and the slightly larger 4521 from the Q12 dissipates about 6 to 7 watts. This sensor is actually much more power efficient than the sensor used in the Chronos 2.1 HD. That runs at about 1/6 the pixel rate. Actually much less, considering if you actually operated the sensor at full speed, which we're not even running the 4521 at its maximum capability, and they already this sensor dissipates about the same amount of power as the 1080p 1000 sensor in the 2.1. And for those of you who like die shots, and that concludes the teardown of the Chronos 4K12. I hope you enjoyed that. Now I'm going to put the camera back together and give you a preview of the user interface. And yes, it still works. I'll give you a quick rundown of the user interface here. What you're seeing here is still a early beta software version. Things will probably change between this and the final release. Resolution select screen is pretty much the same as the Chronos. On this version, is just you can only select 4K or 1080. There's still some work needed to be done to implement the fully configurable resolution in the FPGA, and the frame rate exposure is pretty much all the same. White balance, you can choose from some presets or set custom based on a sample point in the middle. Exposure time is adjustable through there. And if you have a few new things, there's a histogram, there is an overexposure indicator. And in system settings, we've completely revamped that. Brightness control, you can set a few things like what units your exposure is in. You can view the storage, like how much is the capacity or the utilization of the internal SSD. You can format cards, checked devices, network configuration. You may have noticed there's no Ethernet port on the side of the camera. Most users never actually use Ethernet, and in this case, for users who do want it, you can just get because the Linux in this is much more modern than the one in the 1.4 and 2.1, you can just put a USB-C to Ethernet adapter to achieve that functionality. Also things like USB Wi-Fi adapters. So info about the camera, and then various things we can use at the factory for running calibration, etc. And take a quick recording. Go and play that back. Playback screens have been completely revamped. The usual mark in, you can scroll through, mark in, mark out. Saving, right now, given this beta software, the pipeline to perform saving to H.264 is not complete yet, so right now it only saves Cinema DNG, but the H.264 will be done by release. And yeah, the encoder is much faster in this. It'll save 4K at 60 frames per second, and that should scale higher at lower resolution, so it should be able to save, for example, 1080p at 240 frames per second, so 4 times faster than the previous cameras. There will also be a file browser, and although it's not implemented yet, you'll also be able to play back saved files on the camera, which is something you couldn't do on the previous camera. Well, of course you could, in both of them, you can review the video that's stored in the RAM buffer. Yeah, that pretty much is all of the UI I can show you right now. This will be fleshed out pretty significantly before the initial release. I hope you found that overview, teardown, and demo of the Chronos 4K12 interesting. I'll leave you with what probably my favorite shot from one of the initial beta testers. Thanks for watching.